Okay. Good morning, everyone, and welcome to this second day of the conference. There are still someone coming floating in now. But anyway, we have to start to follow our program. And the first speaker today is Dr. Alberto Michelini. He comes from Italy. He has a PhD in geophysics from '91. He's currently a research director since 2003 at the National Institute of Geophysics and Volcanology in Italy. He is now also a director of National Earthquake Center in Italy. And he's working with the real-time and offline analysis of large data volumes. And that's also what he's going to talk about today. His talk is called Data Practices in the Solid Earth Sciences. Please.
Thank you. Thank you very much. I would like to thank the organizers for inviting me to give this talk. And so I will try in the following slides to provide an overview of what we are up to on one side in seismology and on the other side in EPOS. EPOS is the European Plate Observing System. It's an S3 infrastructure which is now going into the implementation phase. And critical to this is the fact that it deals with data and the organization of data and the products that can be obtained from the data. Okay, this will be the second part of my talk. I will come back to this again anyway. Does it work? I have a little difficulty with the... Okay, let me see if I... Sorry about this. It's... maybe that, yes, it works again. So, who am I? I'm a seismologist, a geophysicist by training. I work with earthquakes since, well, a long time. I would say nearly 30 years. I've been involved in EPOS, as I just said. And also in these past years, since, say, 2010, more or less, I've been involved in the NERA, UDAT, and VERCHA projects. And since last year, I've been appointed director of the National Earthquake Center, or INGV. What is INGV? INGV stands for National Institute for Geophysics and Volcanology. It's one of the largest research institutes in Europe. We have about more than 1,000 people that work in it. About more or less 500 are PhDs in geophysics, geochemistry, seismology, and volcanology. And also, what we do is a service for the Italian Civil Protection, which is for seismic volcanic surveillance, and recently for tsunami alert in the Mediterranean Sea. And also, two of my colleagues are coordinating the EPOS and EMSO infrastructures consortia, which have been approved by S3, and they are now in the construction phase, or they're about to start the construction phase. So, the talk summary is as follows. So I will first give an idea what the National Earthquake Center is, the goals, what it does, organization. And in the second part, I will concentrate on the importance of the data. So the backdrop you see here, it's one of the main buildings that collapsed in Aquila. And this is something we don't want to see any longer. We would like that the next generations do not see or will not occur. Unfortunately, if we look at the number of earthquakes that have occurred in the last decade, we always had a lot of fatalities, a lot of collapses, and as I said, too many deaths. So if we look at the, I'm sorry for the quality of this picture, but the number of collapses is very large in this city. This is actually not a city, it's Olna, which is a little town in the Apennines who was hit by the L'Aquila earthquake in 2009. But this is not surprising. If we look at the actual distribution of historical earthquakes in Europe, in the Mediterranean, what we see is that there is this whole part here that goes between Italy, Greece, and Turkey that has been hit by earthquakes, that has been struck by earthquakes several times in the past. On the other hand, I must say also that since we have a long history, there is a lot of detail about, because really Europe is a cradle of our civilization, at least for the Western world. We have a lot of, we are able to put together the data in order to reconstruct or to figure out where these earthquakes have all occurred. So this is a very important piece of information, and we will come back to this. So what are the tasks of the National Earthquake Center? So what we do, we have a rapid and efficient seismic monitoring service. We do the tsunami alert. Actually, we are about to start the tsunami alert. We are right now in what we call testing mode. And also, for doing these two things, we need data. So we have to acquire the data. The data that are acquired need to be archived, preserved, curated, and of course, we need to have products that are, so everything you need in order to discover the data, access the data, and do analysis on the data. So more in detail, so what do we have at NGV? We have about 250 broadband stations, which are a particular type of instrumentation for acquiring the wave field, and 140 strong motion. Strong motion is, it says the word itself, is to record very large ground motions that follow a larger earthquake. We have the Mediterranean Network, MEDNET, which is started in late 80s. It was like, you know, it was a visionary project that included all the all the countries around the Mediterranean. It's composed of about 20 stations. To some extent, we are still maintaining it, but it's also, I wouldn't say obsolete. It's just that at that time there was only this network. Now there are so many other networks that it's not really needed any longer to some extent. And also we have the GPS network. GPS, again, started in the 90s, and now, I mean, it's besides those that you have on your smartphone, there are, and you will see in a moment, there are very sophisticated equipments for measuring the deformations and actually the displacements at the millimeter scale in order to actually see, you know, what are the movements of the surface of the Earth. Then we have we are part, of course, of a federation, because this is something that will come back in the second part of this talk, which is anything we do is really, it's not that there are the seismologists of Italy, the seismologists of France, or those of Scandinavia. We work, at least for larger earthquakes, always on an international scale, a global scale. It's interesting to see that this occurred since the very first instruments, seismological instruments had been deployed in the early 1900s, when there were, you know, the different observatories that were exchanging postcards written, exactly the time which were recorded at different phases or the different amplitudes, or they were actually drawing by hand the seismograms that were recorded and sent to the colleagues in other observatories. So it's this is the way it works. It's been always like that. And so we do the archiving. So when I say ADA is the European effort to federate all these different archives. Then we have GPS and satellite interferometry data, and we have a number of products that we produce, and we have web pages and web services that we are still, I always consider insufficient from what we do, but at least we have something. There is always something new that we had to do. And let me say, I always feel they were a little bit behind, but this is just another matter. Okay, this is the national network, seismic network of Italy in 1985. There are about 50 short period stations. It was a completely different world when we compare to what was in 2010. In 2010, we have about 250 stations, and we have 130 accelerometers. So it improved quite a lot since the early 2000s, more or less. Then, if we look at now, this picture was taken yesterday evening. This is basically the same network. These are, but the addition that you see here is on the color. Here, each square corresponds to a seismic station, and the color is proportional, or actually depicts the actual latency between the data that arrive at our center and when they were recorded. So that means that all the green one here, they have a latency of less than 10 seconds. So that means the transmission, so the data are acquired by the data logger, and the data logger transmits the data to our center, and then it arrives to our servers, and it's in less than 10 seconds. Of course, you see the black ones, or those with the dark colors, are either stations that are not working, or they have very large delays. But overall, what you see is that the status of the network is reasonably good. There are areas that are much more monitored with respect to others. This is because there are areas that are of particular interest where we have installed many more stations. As well, there are others like Sardinia where we have a very small number of stations because there's the potential for earthquakes is very small. Okay. From seismology, these are seismic stations. These are the combined seismic and GPS stations. So GPS stations are very important to record the actual deformation that is going on. So here what you see, this is a classic example of an installation with a GPS antenna. And here you have we have the satellite telemetry here, the GPS receiver, the seismometer, the accelerometer, the solar panels for the power supply. So this is more or less a standard installation, and you see that it's what we have played here. If you look at this, it is we play with redundancy. We know that there are things, some of the stations, sometimes they fail, so we have, between quotes, many more to some extent than what would be needed for the actual monitoring we do, because we already know that sometimes it takes a little bit of time for the technicians to go and maintain all this. There is an incredible work in maintaining a network like this, as you can easily imagine. And this is some of the results of what you obtain, just using the GPS. What you see here, look at these panels. There are 3 panels here, and you have the displacement field, the strain rate, and the fault mechanism. Okay, the displacement here, what you see, these arrows that are here, you see they are larger toward the toward the right, which is, say, the northeastern side of the Apennines, and basically there is comparatively no movement on the others. So it means that there is an extension going on. And those earthquakes that you actually see in the third panel are just the result of this extension. The L'Aquila earthquake was, in fact, a normal fault in which there was extension. And the actual deformation that gives you, it's a pure number because it just gives the ratio between what has been the extension over the actual length. So that delta over length, it tells you that along the Apennine chain there is ongoing an extensional process. And so what we are trying to do is to build this kind of maps throughout, in order to throughout Italy, in order to understand all the relative movements. Okay. This is instead a picture of the seismicity. This picture was made at the end of 2012. You see the latest, the area of L'Aquila here, the area of the Emilia earthquakes, which occurred in 2012. But what you can see is there is basically starting from the northeast of Italy, the Friuli area, where I actually come from, more or less, since I'm from here, from Trieste. And it borders basically all the different, the whole peninsular Italy. So this was for 2012, but then if you look at the 2013 seismicity, it hasn't really changed that much. You see that it's basically what we record in 1 year. We have 21,000 more earthquakes. And for instance, last year, which was very rich actually in not so strong earthquakes, but earthquakes have been effectively felt. We had one earthquake in the Lunigiana area near La Spezia, which was larger than magnitude 5, and several magnitude 4s. So this is another picture instead taken from the NERA portal. It gives you an idea of the largest earthquakes in the Mediterranean area. And here instead I will spend a few words about how we do this surveillance work. And this is basically, these are a number of snapshots, or actually pictures, of our seismic center. And we have, basically a big video wall, like in this picture over here, where we have on the upper left the status of the network. We have, say, the status of the seismicity in Italy, and then we have like a zooming into particular areas where there is activity going on. So. And on the other, on the bottom left, what we have is instead it's our tsunami alert system for global monitoring of earthquakes. So this is just snapshots of the interface program, the graphics that the people who are sitting in this room, which I will talk in a minute, have in front of them, so that they can actually do the work of revising the automatic location. So because there is basically what you have is you have these streams of continuous data that come in, they are enter into our servers, they are automatically processed, and there is an automatic detection. But as any automatic system, it has to be validated. And given the importance that earthquake detection has in Italy, so there is always a manual and expert revision of what's going on. And the seismic centers, so these are different snapshots of the same room. What you see, it's really also a very lively place within INGV, because it's something that it's, there are always people gathering there besides the people who are on duties. because there is always something going on, put in very simple words. So how does it work, the operation? We have, say, basically in that room that I just showed you, 3 people, 24 hours a day, 7 days a week, and those are 2 seismologists and 1 engineer. And then we have a number of people who are on call. So there is 1 chief seismologist who is actually, he's on call, but he's in charge of the work done in the room. So anything that doesn't work or there is something to be done, the people who are in the room, they have to call the chief seismologist for and ask for support. Then we have what we call the reservists, those people that are, in case that one or more of these is sick for some reason or cannot attend, so there are always people who can substitute, replace the person. And then we have still on call 1 person that is in charge of the IT seismic procedures and 1 for the network. And finally, 2 people for a rapid mobile network deployment. So in case of an earthquake, there is a particular area where maybe we don't have enough stations, there is always a group of people that goes there with a few temporary seismic stations to be installed and then connected with the data that will be transmitted to the center. Also, especially recently, we've been paying a lot of attention on redundancy. And in case that something occurs in our headquarters in Rome, we have basically replicated our services in the sede Irpina, which is another center, or say another headquarters of INGV. Well, not really headquarters. It's a center affiliated to us. So, and also we have a replication to Catania. Catania is one of our volcano observatories. So basically, the idea is always never to be in a position which we have something that breaks down and we don't have any other place where we can do the job. Okay, now I will go through very quickly just to give you an idea of what's going on. For this is a case of for a tsunami alert. I mean, I mentioned earlier that one of the things we do, and here it's an example of an earthquake that occurred about a year ago near Crete. It was magnitude 6.6. And at that time, we were not operational as tsunami alert, but this is, probably our best case to train people for tsunami alert in the Mediterranean. So what you see here is, just please look at this picture, which gives you essentially where the epicenter is, and the larger circle you see here is at that time the wavefront of the P waves. The P waves are the first waves that are propagated, the fastest waves that are propagated by an earthquake. So, and the thinner one are the S waves. So what we see here after 2 minutes, these are the first stations that have basically recorded the earthquake. They have been already in automatic location. Then we go on. This is 1 minute later, and you see that there is already first identification of what the mechanism of the earthquake is. There is a fairly good idea of what the actual magnitude is. We are talking about around 6.6, 6.5. This is given by the measurements that are made on the actual records on the seismic stations that you see here as rectangles. So we go on and we see how these measurements are progressively done And in the end, you get more and more recordings, and after 7 minutes, you already have, really a very good idea of what is the actual earthquake. So we go on 9 minutes, 14 minutes. 14 minutes, we have, a good measure of what is the magnitude, what is eventually the duration of the source. And, but these are all, details, seismological details. I showed you this picture for one main reason, is that you acquire the data, you have to do quality control on the data automatically, so you have to have procedures. You have procedures that do the actual, the detection and the location of the earthquake. So there is a full, there is a pipeline of operation that have to be done. And these are on the same data that then you may eventually use for doing your research. Let's go on. So I said that this was for tsunami alert, and this is basically then the actual message that's generated automatically. In this particular case, if we were operational, we would launch what it's called a watch state for some of the nearest, near the coast near to where the earthquake is. One note is we are not the only ones, of course, in the Mediterranean. There is also the Greeks and the Turkish and the French that have also set up a tsunami alert system. Okay, let's go on. Dissemination. One thing that you understand for sure is that anything we do, it's not just communicated to civil protection, but we must provide it to the public, so that because it's like an expert. What we are trying to do is to avoid. If you would give the information as quickly as possible, and you're careful about giving it, you avoid many other things that can happen. So other people, they start to give information improperly. So this is our channels. We have a web page, we have a database, we have an iPhone app. We are present on Twitter, we are present on YouTube. We have a blog which is called INGV Terremoti. We are present on Facebook. So it's we use for the same information different channels, so that people can actually immediately grasp what's going on. And of course, we have also other more IT services that allow people to download our data. In this particular case, this is it's called QuakeML. It's a derivation of XML. It's a format for providing our earthquake catalog. Or there are other ways, our web services for checking the actual status of the seismic stations. Okay, now I go into what is the second part of the talk, which I will concentrate on EPOS and the data issue. So this is it's a fundamental part, because this is we are not talking any longer just of seismology. We are talking about the solid earth sciences as a whole. In the next picture, I will show you something which can be an abstraction, but it's basically what happens with the data. So we have clearly an acquisition time with the stations. We have a transmission. I talked a little bit about that. Then the data get collected in some place, and where after this first collection, the data are pipelined into some, say, real-time analysis, for instance. But the data also, they require a number of services for, in order to have the services properly working, you need to properly qualify the actual data. And here, the idea of having persistent identifiers, metadata, it's really critical. So that if you do this properly, then it's possible that you can easily exchange with other communities, not only within the earth sciences, but also outside. And then also, you have to take care of all what concerns the storage and you have to take care of accessibility. So these are all services that we have the mandate to do, and we must do it, given also that we are a public institution, and we have to do this, provide this for free. So just a few words now about data that are, when we were starting with all these EPOS that I will talk in a moment, were critical. And it was the idea of integration, the idea of interoperability, to have open access to the data, to acknowledge the source of the data. This is another critical question, because it's very often some people do not give data away because they are afraid that someone is kind of stealing their data. Instead, we must always have a way to properly acknowledge the use of the data. And of course, we have to, in order to have progress in science, we have to acquire data of, always of better quality, and this is, related to the acknowledgement. We must be able also to reproduce the results that we do. So we had to provide, whenever we do something, we must put in a position the audience, whoever is reading our paper, to be able to reproduce exactly our results. This is something that, especially when you have a large amounts of data, very sophisticated techniques, often it's kind of overlooked. But this is something we should definitely spend time on it. And also, the other thing is that by developing a new infrastructure, a new e-infrastructure that allows you to deal with data and products in a better way, you focus much more on the physical phenomena rather than on the data organization or changing the formats or things like that. Really, for a scientist, are to some extent a waste of time. And also, think about in terms of implementation. Implementation of what? Think about all the money that has been spent to set up the infrastructure, and these are required to be maintained at the national level, and this is a big effort. At the same time, we had to make it clear to society that all these efforts are ongoing, because otherwise, if we think that we as scientists, we are a step above the others, we lose. Because it's, I think we lose our authoritativeness. We had to be able to explain as much as we can what's going on in simple words. So, given all this, we started with what we call the EPOS preparatory phase mission. So this was basically, look at this cartoon we have here. I mean, EPOS was basically starting already in the early 2000s with a few projects where people were starting to think about federating the data and the services. Then this is called the conception phase. Then we went to, it was approved as in the S3 roadmap, and then in 2010 started what is called the preparatory phase. But what is EPOS all about? It's a long-term integrated research infrastructure plan. The idea is to put together all the sub-communities that there are in the solid earth sciences so that they can actually provide their data, share their data, but to have a communication between all of them, so that if you make a search for some particular region, you can find all what is available in that particular region regarding the data that you need. So, and the idea behind is that we had already an incredible number that you will see in a second of facilities in Europe that were acquiring data. But the problem was that we had an incredible fragmentation. And also, we realized that it was important we had these timescales for studying our phenomena, which are which in time they span from the thousands of seconds to millions of years, if not longer. And the scale length this is in time, this is in space. You go from the micrometer to 1,000 kilometers. So it's really a complex thing. And on the other hand, there are different, when you go from the laboratory experiments to the continental size, there are things that are studied that have, they match. When you study, for instance, the rupture of a fault, you do it at the laboratory level to understand the details of what's going on using, your machinery. And on the other hand, you have the real earthquake that occurs at regional scale. So, EPOS framework. So, we tried to put together all the seismologic observatories, the volcano observatories, the geologic and surface dynamic data, geodetic data, other data that are acquired like gravity, magnetic data, OBS data. OBS stands for Ocean Bottom Seismometers. Analytic and experimental laboratories, satellite, geomagnetic, and other infrastructures. And the whole thing requires ICT expertise and research infrastructure facilities, so that actually they go across all these different sub-communities. And here we have, if you look, really a plethora of different projects that have been supported primarily by the European Union. And the problem is not that there is not enough money. The problem is that is to link all of them within the same context, so that you don't have that, for instance, UDAS does things that Verce, which is nearby, doesn't even know. So the problem is how you integrate this in the best way. And here, it's just a look at our facilities. Think about this. This is for an astrophysicist, he has a telescope. In our case, we have a bunch of instrumentation. We have seismic GPS stations throughout Europe, and our goal is to link them together so you have one single infrastructure that you can use for studying the Earth. And here it's another view of the same picture, but look at the incredible amount of facilities and the stations that are available, and think about the fact that you don't want that these things are disconnected from one another. So these things this was realized since a number of years ago. There is in seismology, which is between the different sub-communities, probably the most evolved one. We started with the European Integrated Data Archive early in years 2000, more or less, and the idea is to put together all the seismological data. And this is the situation now. I mean, and we definitely have a fairly large amount of data that are all combined together, and at one of our centers, one of our nodes, if we make a request, you can have the data of all. This is the idea of the federation. So now let's look at what I consider, between quotes, my dream. I'm not sure whether I will be able to see this, but I think that what will happen in the next years is to put the researchers in a position that they will be able to, say, discover, retrieve different types of data. In this particular case, you want to request a particular earthquake. You want to obtain what we call the moment tensors, which are a particular type of analysis that is the result of analysis that is done in order to calculate the focal mechanism. You want to have geological data for the same area. You want to have how it was felt, that particular earthquake, so the microseismic fields. You want to retrieve what we call the shake maps, so the level of ground motion that was observed. And here I don't go through all this, but the point is to have a central place where you can actually obtain all these different informations. And in the end, remember that since we are scientists, we want to compare what is observed with what we model. So we must be in the position to be able to model our data, at the same time have the observations to check whether that is correct or not. And eventually, if it is not correct, correct the models that we use. Okay, so what is EPOS then organized? The idea is to have the following. It is let's look at the bottom. We have all at the national level, you have all the facilities that I showed you. Then each one of the sub-communities, so it could be the seismologists, the geodetists, the volcanologists, they organize themselves as a single as a community. This is what is called the thematic core services. So each community organizes itself with certain particular services it wants to provide, but then they have to organize themselves in a particular manner so that they become transparent the moment in which they are integrated with all the others, and this is what we call the EPOS integrated services. So it's basically you're going from the granularity of the nation, you go to the country, then you go the granularity of the actual teams or the communities, and then to the full integration. This is what has been done or it's going on in seismology. We have what we call the waveform data. These are the raw data that are acquired by the station. Then you have some first products, like automatic products that are obtained. Then there are more evolved products that are related to the calculation of hazard and risk, which take into account all that's calculated in this second pillar that you see over here. And then we set aside the computational seismology part, which is an important part, because without computations you don't go very far. This is more or less the actual basic model for the infrastructure. From the bottom again, just to do, these are the raw data. The raw data get progressively organized and qualified with persistent identifiers, for instance. You have the first services that allow you to have access and retrieval of the data, and then here you have progressively more sophisticated products. Of course, this has to have a trust, so some authorization, authentication infrastructure, and also you must have some ways to acknowledge how the data are used. So it's some kind of accounting. And the user sits on top, and with a number of services available, he can certainly, do research in the best way, and especially faster than certainly the way we did it when we had to basically work out from the very bottom of the pipeline. This model here, it's very similar to what is done in UDAT. UDAT is this EU project in which, again, we have the data generators, we have the users, you have the community support services, the thematic services that I mentioned earlier, and you have common data services at the bottom. And these common data services are basically those services that are common to all the disciplines. So now I go just to give an example of the actual, the raw data. We have some level 1 data. We have level 2, which are analysis. And then we have level 3, in which we have, say, for instance, the seismic hazard map. And then to the part of the computation. So conclusion and afterthoughts. So there are so the EPOS communities feature very different levels of data organization development. This is something we realized from the very beginning. There were communities who were very well evolved, some were not. So the problem, one of the challenges was put them together. Each sub-community they had their own services in-house developed. So they are kind of reluctant to say, hey, now I had to do it again. This is a very important fact, that is, once you put so much effort in doing something in your little community, it's difficult that someone else from outside goes there and tells you, oh, but you can do in this other way. So it's, in fact, the difficulty is also that many of the communities, they're really striving to maintain the services they have. So the idea to have new ones, it's even worse. Also, there is the idea that many of the communities think they have the best services, so they don't think that anything else is needed. And they like to be their own little community, whereas now the point is to be transparent to the neighboring communities and to be able to provide data that maybe someone else can use. And the other thing we notice is that it's a slow process to introduce new processes. I mean, new concepts. I mean, it's really difficult. There is a problem with the jargon that's used. For instance, the IT used one jargon, we used another one. But what we found is that even if you have this viscosity, it in the end, by repeating and repeating, things do get assimilated at some point. And it's what I call it's a positive maturation process. Overall, building an infrastructure is very demanding, given the diversification of the different communities and different data organization. The other thing I wanted to say is that we should never lose what has been done before, and we must capitalize on what is existing. The idea of having thin layers that basically glue whatever has been done before with, say, more modern developments, it's, I think, a very important thing to consider. And we must have a continuous orchestration between the different scientific communities and the ITs. Well, here are just a few things about the communities within the UDAT project, in which we were kind of ambassadors. And the last point is the communities are undergoing a positive maturation process, and the ITs are understanding progressively the problems of the formers and envisaging solutions. A mutual trust and synergy is fundamental. Thank you.
Thank you for a very interesting talk. Are there any questions from the audience? It's too early in the morning. One question, Jacqueline.
I was wondering, at the very beginning of your talk, you said you wanted to avoid the disasters like L'Aquila, where wonderful buildings fell down and killed people. But, I mean, the architecture, the buildings themselves, you can't do anything about them, really, can you?
Well, actually, what you can do is, I mean, if you had a lot of money, an investment would be in retrofitting these buildings. But it's a humongous amount of money and work that's needed. But before that, that is what we are really striving for, is that people have to be aware. I mean, it's aware of where they live. Because the problem is, and I throw a stone in the lake here, keep in mind, the politician, it's if he can provide money to do, say, the retrofitting. Say that an earthquake occurs, okay, nothing happens because the building was retrofitted. So it's not so important on the news. Nobody got killed. On the other hand, if he invests and nothing happens, still it's an investment, and you know what I mean. He wasted, between quotes, money in something, but nothing happened during his time in his position as whatever mayor or whatever he is. So a little bit, there is a certain amount of perversion in all this. So there is not really very much interest in putting money in doing the retrofitting. And also the law right now in Italy, it is that you have to build new buildings according to the law. And there is not so much about, obligation of retrofitting.
Okay. Thank you.
Okay, that makes us possible to keep the time. Thank you again.
Thank you.
Okay, let's move on to the next presentation. The speaker is, name of the speaker is Sebastian, I think it's pronounced Setterick. Okay. He holds a Master of Science in Telecom from Lille in France. He is the Wi-Fi Network Service Manager at CERN, and he's also been the project leader of EduRoam at CERN. So please, Sebastian. His presentations is called Large-Scale Campus Wireless Networks, Developments, Opportunities and Strategy.
Thank you, Peter. So, good morning, ladies and gentlemen. So, I would like to thank first the organizer for inviting me. It's a royal pleasure for me to be there today. So, as a Wi-Fi service manager at CERN, I have been the witness of a large and very fast evolution of Wi-Fi networks. So, as a Wi-Fi manager, I'm taking care of the deployment and operation of a large Wi-Fi network, so hundreds of buildings in surface, but also all the infrastructure on the underground facilities of long tunnel, all the caverns and so on we have at CERN. And also I'm taking care of EduRoam services. So this fast evolution of the Wi-Fi Wi-Fi demands has posed a lot of impact on the large-scale Wi-Fi infrastructure. So what are the best practices? What are the opportunities and what are the challenges in deploying and managing such a large infrastructure? So I would like to present you how we do it at CERN, this evolution of the network. So the Wi-Fi evolution. So since 10 years now, the Wi-Fi has evolved very, very fast. The technology have made a lot of progress in security, in reliability, and in performance. So since the first standard, the .11g, as the performance has been multiplied by more than 50 with the latest standard, the .11aca. And the second generation of the standard, the AC Wave 2, is promised to break the 100 gigabit over the wireless. So this offers us new opportunities in terms of access connectivity for our end user. It's not only the success of the improvement of the performance of the wireless network which is responsible for its success, but also key technology like the multi-touch screen introduced with the iPhone, or the development in the technology like lighter electronics, lighter mobile devices, the increase of the battery life has really improved the performance of the mobile devices and is responsible for this great success. So the great success of these mobile devices have put a lot of demands on the wireless connectivity. And this is not going to stop. According to Gartner, in 2013, more than 50% of devices sales on the market were coming without Ethernet connectivity natively. There was only Wi-Fi. Wi-Fi is becoming the primary network access for numerous devices we have on our campus networks. So what's happened today? So we start to have more and more wireless devices connected. People start to have more devices. So I guess most of you has at least one laptop or one tablet with one smartphone connected or even more. So these devices are going to be always connected anywhere at any time. They generate a lot of bandwidth because several applications are running at the same time on the devices. So this put a lot of constraints on the infrastructure. So we need to support with bandwidth, but also we need to provide a non-stop operation. Our users are less and less reluctant to problems on the wireless infrastructure. Another revolution is going to happen as well is the Internet of Things with wearables like Google Glass, but also the industrial systems. So we saw more and more industrial devices natively coming with Wi-Fi enabled, and people want to use it because it's convenient, it's flexible, it's a wireless sensor. And connecting all these devices together will bring new application, new promising application like smart campus. This will enable us to do a lot much more in terms of managing large facilities, in terms of efficiency, in terms of smart grids, access control, and so on. But how this evolve at CERN? What are the evolution of Wi-Fi network I have seen at CERN since a lot of years? So in early 2007, the infrastructure was composed of 300 access points, and it was serving about 600 users daily. 7 years later, now we have multiplied by 10 this number. So we have more than 6,000 simultaneous users on the network, and the network see more than 12,000 unique devices per day, for a total of 1,500 access points currently running on the facilities and always increasing. So this fast and large evolution poses a lot of constraints on our infrastructure and has imposed us to review our strategy. So how we will have to engage the resources, how we have to reorganize our services, and what are our strategy to support this always increasing demands. So as a service, Wi-Fi service manager is a challenge for us to cope with these demands. But it also brings a lot of opportunities for our users at CERN, for our community, but also for us. First of all, the way we are working, the way we are collaborating is evolving thanks to the mobile technology. And it's happened to see at CERN some new kind of offices, like you can see. Wi-Fi connectivity brings a lot of mobility, so you can move easily your offices to a new place where it's most convenient for you to work, to go to the library. It's also very convenient to extend the wireless networks in very difficult, harsh environments. This is, for example, NCAP detector of LHC detectors. As you know, you might know the LHC is at 100 meters under the ground surface. And this big part with weight a lot of tons have to go down through 100-meter tunnels done. And the distance between the walls and the detector was at some point few centimeters. And they installed a sensor all around the detector with a station there to monitor and to be able for the operator to bring the device down without any incident. And also, Wi-Fi network or wireless network in general brings a lot in terms of real-time collaboration. Since 2012 at CERN, we are operating and doing a lot of maintenance work on the LHC facilities. And we have deployed for this specific work more than 300 access points inside the LHC tunnel, inside the 27 kilometers of LHC tunnel, to provide the team with a reliable and efficient wireless connectivity, thanks to LTE, UMTS network, and Wi-Fi. And the benefits of this was real-time collaboration. So people working there was able to access the right data anywhere at the right moment. So this has improved a lot the responsiveness of the team and also their motivation to achieve the work and provide the work with great quality. It can bring us also new opportunities. So we almost have one smartphone. So if you can make inside the building the same call at a cheaper price with the same voice quality, why we should continue to use these old phones? Real-time location systems are also opportunities with full wireless coverage in the buildings. When we talk about real-time location system, most of the time we think about navigation inside the building, finding his way inside the large campuses to find the right room. But it can bring us much more than this. It can bring us asset positioning, assets tracking. Let's give you an example. Still for this LHC maintenance period, a lot of technicians was running in the facilities with specific equipment. And it's happened that one technician forget at some point to put back a radioactive vacuum cleaner. So this is very, very sensitive equipment. And we spent more than 1 week to find where was this vacuum cleaner. And with such a system, it would have been very, very fast to just track this equipment to know where it was stored and discovered that it was stored not at the right places, but at other places. Another opportunities of real-time location system is context awareness. So you know where the device is connected, in which location, in which facilities, and we will be able to target specific content to specific devices depending on their location. But I think the big opportunity that the new technology, and especially the .11 ACs, will bring is the possibility to build a truly mobile environments, so wire-free workplace. Why it is the right moment? Because now the technology is ready. It's ready because the performance is there. You can have up to 1 gigabit over wireless. This wireless now is secure enough, so we have all the mechanism to perform true authentication, encryption, make sure that there is no intrusion of the system, there is nothing disrupting the behavior of wireless connectivity. The systems are becoming more and more reliable, so the manufacturer put a lot of effort of providing us with redundancy mechanism and a control system. It brings also a lot of flexibility, so with one single wireless infrastructure we can accommodate different types of services. So you can of course provide connectivity for your staff, for your students, for your employees. You can also provide on the same infrastructure connectivity for voice, for guest access, for EduRoam, but also connect their industrial devices or other equipment, always on the same access point, on the same bands, on the same infrastructure. And of course, the management system have improved a lot to manage really large-scale infrastructure. And why it is also the moment to do it? Because the demand is there with the evolution of devices and the mobile devices. So, but this brings a lot of challenging on the infrastructure. How to deploy this and make it sure that it will work all the time, especially if we remove the cable and go for a truly mobile wireless environment. So, is this familiar to you? You arrive, you connect to your favorite wireless networks. You have a full signal, so everything seems fine. But what's happened when you want to reach your favorite website? It takes a lot of time to load the pages. Why? It's not the server which is dead. It's not the signal which is bad. This is something else. It's much more complex than this. The quality of a signal reception is not the single factor to provide you with a performant connectivity. High performance connectivity requires, of course, a good signal level, but also a clean radio frequency spectrum, so nothing should disrupt your wireless communication. You need also to have a low contention. If you have too many devices, too many users wanting to communicate on the channel at the same time, it will not work. Also, your device has a great impact. The quality of your driver, but also the quality of the hardware inside your devices is really important. So it's happened to me that in the same condition, the system do not deliver the same performance. I have one time that one of our physicists at CERN bought a new MacBook Air devices. And before he has a MacBook Pro. He put the two devices close each other. The MacBook Pro was working like charm at full speed, and the MacBook Air was having connectivity problems. It was just because the driver was not the right one on this MacBook Air, which was not able to perform equally in the same condition. So all of that to say that airtime fairness is the key. Wi-Fi work on radio waves, and the amount of spectrum we have for Wi-Fi is limited resources. It's limited, and you have to share it with other devices, but also with all the Wi-Fi devices connected on the infrastructure. As I say, the Wi-Fi is running on free bands, so bands without licenses. So this means that other devices, other technology than Wi-Fi can use it. So we can find on the Wi-Fi band Bluetooth devices, DeX phones, but also microwave ovens or other type of devices are running on it. So it's happened now that more and more devices are going mobiles and are not necessarily using Wi-Fi. So this means now that the 2.4 GHz band is completely crowded. And contrary to the wired, we cannot neither manage the medium nor the end user devices. So this causes us a lot of constraints to manage properly this infrastructure. But there is rules and techniques to gain control over this. So large-scale Wi-Fi is really complex. It's complex because there is a large diversity of different types of end-user devices. It's complex because of the infrastructure by itself. All the buildings have a different shape. We can find different type of interference, different type of propagation inside the building. And the environment is really, really dynamic. People are moving, the way the waves are propagating inside the environments are changing. Everything is always evolving. And also the end user expectation has increased a lot. Before we have few devices connecting in a meeting room, now is very common to have hundreds and hundreds of devices connected in an amphitheater, for example. The user expectation also have increased a lot. Now they want on Wi-Fi the same network quality than they have on the wired infrastructure. Security and policy are also really, really important. So how we do deal with this at CERN? So how are we going to move forward on almost 100% wireless environments? So first of all, we need to get the most out of the Wi-Fi technology. Then we have to also adapt the resources, the budget resources, the human resources, and so on, the organization. We need to have the possibility to deal with any interference, any other system can emit some radio waves. So we need to have a full control and the right to have a full control over the spectrum. And we, of course, we need to apply the best practices and project management rules. So let me explain you a bit of what is new with .11 AC technology. So we can see the AC technology as an evolution of 11N technology. The difference are it is working only on the 5 GHz band, so this is good because we are getting rid of interference we have on the 2.4 bands. It brings a new higher rate modulation, so with the same interface we can put more bits inside the same channel, so we can transmit faster. He introduced an explicit beamforming. So what is this? Beamforming is the possibility that the equipment has to focus the transmission to a dedicated device. So this improves wireless link quality. Like you can do with a lamp, you focus the light, then the access point now has a possibility to focus the transmission. Is using also a larger, I would say, pipe. Before we are using 40 megahertz bandwidth, so we double it. So we double basically the capacity, the performance of the channel. So it will provide us, so with 40 megahertz bandwidth, a real performance of 350 megabits compared to the 200 megabits we have with N technology. And the second generation is going to provide even more performance, up to 900 megabits, so close to 1 gigabit over wireless. But the main improvement we will have with AC is a multi-user MIMO. So the multi-user MIMO is a very great feature. It's going to move the Wi-Fi technology from the hub to the switch principle. So on the downlink only, for example, with 4 antenna, an access point will be able to transmit up to 433 megabits up to 4 devices simultaneously. Before, each device has to wait its turn to get the data. So now with this technology, up to 4 devices at the same time will be able to get the same bandwidth that we have for the N technology in the past. So how are we going to migrate to AC technology? So this new modulation rate is, the range of this new modulation rate is few meters only, because it's much more complex, so you need to have a very, very, very good signal to achieve it. But as the the technology performance improves, the chipset has a better quality and sensitivity, so we get a better performance than the previous technology at the same range. So this is good for us. So if you have done high density deployment using the N technology, you can simply swap the N access point with the SC access point, and it will work. No need to redo the full radio frequency planning. But which bandwidth should we use? Should we continue to use the 40 megahertz as for N? Should we use the 80 megahertz as the AC offers? Depends on your environment. So 40 megahertz work very well in multi-floor environments because we have 4 channels. So it's easy to reuse the channel in 3D dimension without co-channel interference. But if you want to get more bus throughput, you need to use the 80 megahertz one. And if you are going to do high density, so like an amphitheater with thousands of users, you have to use, like for N, shorter bandwidth. So what is our approach? This is a heat map simulation of wave propagation inside a typical building at CERN. So for hot color, it means that there is a higher signal level, and cold color means that the signal level is very low. And basically, we need a minimum of minus 65 dBm for the Wi-Fi to work properly. So before we were placing the access point in the corridor, which was serving basically up to 6 offices. But this approach has a lot of drawback. It has a drawback because the signal goes very, very far inside the corridor, and also is propagate the noise level in neighbor offices that we do not cover, so the access point do not serve this one, is quite high. So it makes more difficult to manage this channel and the planning later. So our new approach is to provide the smaller cells. So we will reduce the transmit power to have the same transmit power on the access point than on the smartphone devices, on the tablet, so around 10 to 12 dBm. So this enables us to have a very strong control over the cells and to guarantee the high throughput inside these 3 offices. So basically, this is what happens if you deploy the full floor. So we have one access point for 3 offices, and we don't put them in front of each other, but with one room aside to provide a homogeneous coverage, but also to make easier the roaming and to mitigate the co-channel interference. So with this approach, we will be able to provide 80 megahertz channel inside our offices. Deploying and managing large-scale Wi-Fi environments need very specific skills contrary to traditional networking skills. So you need to have specific skills for designing the radio frequency design of a wireless infrastructure, how the wave will propagate, what will be the impact of the co-channel interference, what will be the impact of interference in the building, and so on. You need also specific skills for the technician who will do the installation of access points. Typically, this is an installation on one of our buildings outside. So technician needs to have good skills of how to make radio frequency connector and so on, how to ground properly the equipment. We need also specific skills to troubleshoot the Wi-Fi. On a wired, it's more easy. You plug the test devices on the cable, you correlate the information, and you know more or less what could happen, what are the problems. It's a bit more straightforward. On Wi-Fi, as you do not manage the medium, you have to collect much more information, and the source of the problem can be a bit everywhere. Safety and regulation is something a bit new, and we have really to take into account. Most of the time, the access point and the antenna are not installed as a human height, but might be installed at quite high height. And so there is specific safety to take into account there, and regulation also. We cannot transmit anything on any frequency at any power. In terms of resources, what are the differences between doing a traditional deployment as we are doing at CERN and the direction we are going to a wire-free workplace? So we basically compute that we need to double the number of Wi-Fi equipment, but we will save about 45% in terms of Ethernet port and UTP cables. We will need also new skilled manpower to perform these changes, and also introduce Wi-Fi specialized network management system. So at the end, we will not add extra costs in moving from traditional Wi-Fi environment to a wire-free workplace, but we will not save the money neither. Another very important point is the infrastructure. Is the infrastructure ready to support this new high-performance Wi-Fi infrastructure? Most of the access points will require more power on the access point. So we will require PoE plus 25 watts per access point. So this will have an impact on the start point level. So we will consume much more power than before. Also, with AC, the access point will be able to provide more than 1 gigabit. So one gigabit port might not be enough. So today, the manufacturer are not. There is no yet a consensus on the manufacturer to decide if they are using 2 1 gig port, if they are using 10 BST over category 5s, or if they are going something in the middle. And the backbone also is important. Before, the 1 gig uplink on the switch was enough. Today, with AC, we see that 10 gig will be required. And don't forget the cost about the infrastructure. So when we compute what will be the cost for deploying such large-scale wireless infrastructure, it appears that 50% of the cost of installing an access point come from the wired infrastructure. It comes from the cost for pulling the cable, drilling the wall, pulling the cable, building the cable path, and buying the switch. So this was a bit of surprises. This is really important to take into account for large deployments. Policy. If we do a high-density deployment, and if you want to use Wi-Fi as your primary network access, you need to gain a full control over it. You don't want user or anybody to come to disrupt your network. But to do this, you need to ask a lot of questions. So should we allow private access point still in the environment or not? Which type of radio frequency transmitter will be allowed? So are our users allowed to use wireless headphones, for example? What about the microwave oven we can have in the restaurants? So are we allowed to use them at lunchtime or not? If we have electronic labs who have to build different electronics, what is the priority? Is it the research for this laboratory lab or the Wi-Fi connectivity? So this is a lot of questions we have to ask us before defining the rules. and also who will have the authority to act and to decide which devices have the priority over the spectrum. So we've bring you on device which appeared a few years ago. So we have more and more smartphones, tablets, and so on. This has an unexpected impact. So all these devices work most of the time on not even N, on 5 GHz bands. So this is really fine. But it comes with only one stream. So this means that it has a reduced performance over the full capability of the N standard. So this comes, which you will use the same time to transmit the data, but has a lower performance. And also, the hardware of these devices, most of the time, the priority is put on power saving. So the performance are reduced. So this causes a lot of problems in some environments, because most of the time when you go in a meeting, for example, where is your smartphone? Your smartphone is like me now, in the pocket. So the performance of the link quality will be reduced compared to the laptop, which is there, which has a direct connectivity to the access point. So we will have to deal a lot with this problem in the past. So what should we do? Should we ban them? Of course, I think most of our users will not be happy if we forbade this type of devices to connect. So the idea was to go for planning for capacity. The coverage is not enough. It's not enough to have a good coverage in an environment. You need to make sure that all different types of devices, we have the possibility to have a fair access to a Wi-Fi medium. So the goal is to ensure that every devices have a fair access to the resources which are shared across all the applications running on all the devices. So to do that, we need to identify what are the user requirements. Of course, they want to do everything with all of their devices, but we need to put some limit, and the technology allows us to do this. Then we need to compute what are the airtime consumption for all the devices. So we need to compute how many users we have in a room, what they want to do or what we allow them to do. We compute what they will need in terms of resources. And then we are able to forecast the capacity and to design the infrastructure. But to do this, we have to make sure that we will have access to the full spectrum available. The problem is some devices, as I tell you, are using this spectrum. So we can find microwave oven, we can find wireless headphone on the 2.4 GHz band. We can find some Apple time capsule, for example. This has caused us a lot of issues also in the past, because people want to back up what they have on their Mac on these devices, because it's nice. You turn it on, then it's synchronized, and then you synchronize all the data. But when they do that, they consume a lot of resources on the spectrum. So we cannot allow them to do this. And as you might know, for people who come at CERN already, the CERN is very close to Geneva Airport. So we have a lot of problems with in the past with the radar running on the airport for the airplanes or for the weather. Oops. So the goal there is to avoid the 2.4 GHz band when possible and eliminate the RF interference. But of course, we cannot do that for everything. We cannot prevent the airport to run and the plane to fly above the facilities. So the idea to optimize the radio frequency spectrum is to enhance the spectral efficiency. So there is technique to do that. There's a lot of technique to do that and to minimize the co-channel interference. So turning on the features is not enough. For example, the manufacturer has introduced a lot of technology like band steering. Band steering enables the devices to push the client devices from the 2.4 GHz band to the 5. But if you do not plan properly the coverage, and you don't have a good 5 GHz coverage, your device will fail to connect. So most of the systems do not work out of the box and might require a lot of proper planning at the design phases, and also some adjustment and tuning later. So to manage large-scale environments, we need a lot of automation. When you need to manage thousands and thousands of network equipment, even if you are using a wireless controller, which are where the access point connect to it, and then the controller push automatically the configuration, is not enough, because depending where you will install the access point, you might want to deploy different type of service, different infrastructure. You won't have to group them for different groups for load balancing or load sharing, so you still need to automate this process. So we have deployed a very large software that we have integrated into our network management system to do automatically this task. So this provides us simplicity, it increases also reliability. We no longer ever go to the CLI of the equipment, but we have our server where we simply run a command and the server will take care of pushing the right information to all the devices. So when we install a new access point, for example, we configure it once in our databases, then we say configure, and then we will push the configuration to the DHCP server, and we'll push also the configuration to the controller. Then when we will plug the access point, everything will be pushed to the access point automatically and it will be ready to work. So it's much more simple to manage. So how we are going to deploy this? What are the organization? So first of all, we need to prepare a lot what we want to do and how we will deploy this. You need to collect the user requirements. You need to know how are the environments, so what we can do in this environment, what is the existing infrastructure, and take care of all the constraints, especially in terms of safety, how the access, how can we access to the environments. And the citizen might be important in some places. So there we need to set the strategy. How we will provide which type of service we will provide and how we will achieve this. Then we go in the design phases. Contrary to a lot of different sites, we'll do a lot of radio frequency simulation. So we have a software. We modelize all the buildings in 3 dimensions. We set all the building materials properties in this 3D model, and then we run the simulation to see where is the best place to place the access point, which channel we should use, how the interference will go together, what will be the propagation inside the building. This enables us to save a lot of time compared to doing a traditional survey inside and going with a laptop measuring the signal. Because simply there we can drag and drop the access point to see how the propagation evolves inside the buildings. So when we do that, we consider both capacity and coverage, and we design from the beginning for voice, but also for real-time location. This tasks do not cost much more effort to going straight for voice and radio and real-time location because you can just prepare where we will put the access point to provide these services, but you are not forced to deploy it now if you just want to do data. But at least the study will be there and not consume more time. So then we need to verify the design. So for that we do a site survey with a tripod, with technician going in all the offices. So to simplify these efforts, one good practice is really to inform the user in advance, to avoid the user to ask a lot of questions to our technician and make his life easier, and I would say. We analyze the result to validate everything. Then we will plan, build, and test this deployment. So this is the time where we will configure and test all the devices and upgrade the infrastructure. So the goal there is to have access point ready to work once they will be connected. Why we are doing this? So when the technician will go on site to plug the access point, he will see directly if the access point is working or not. For example, we have a lot of problems with defective patches. So PoE need only 2 pairs on your UTP to work, but 1 gig need 4 pairs to work. So if you have a patch with 1 broken pairs, it will fail to work properly. So if the access point is installed in height, it will be difficult to replace it. So that's why we go do this like this. So then it requires a lot of work coordination. And at the end, we check that what we have planned and entities is working very well. We do again a site survey to check that the coverage is as planned, and we optimize if required the infrastructure. So, but of course, when you have deploys, it's not enough. The environment is always evolving and changing over the time. So this is really important to continuously control, act, and monitor the network. For this, we have deployed and build our own monitoring system, so which is able to tell us what is the airtime of each access point, how the access point resources are used. So this is what we can see there. There we can see radio frequency interference from microwave event, for example. Then we can see high usage of the access point, or like this as well. But also these tools enable us to see what are the usage of wireless resources from the end user point of view, from the end user devices. And then we can see typically what are its performance. And we can see there that it has a connectivity issue, for example. So this enables us to do a lot of remote operation, proactive optimization, and efficient end user support. So to conclude, wireless installation requirements will continue to grow. Users will demand more and more wireless connectivity, reliable wireless connectivity. And we think that with .11ac second generation, it will offer opportunities to deploy truly mobile wireless campuses. But this has changed the way the users are using the wireless. It has come from nice-to-have services to a fundamental services that thousands of users in our environment require to work every day. And to make it work properly, this requires a lot of investment in terms of resources, in terms of budget, in terms of organization. So thank you very much. If you have any question.
Thank you. Are there any questions? No questions.
Thanks. Christophe Oldrati from Siena. I was wondering, you were referring to the issues led with the possible contention and the requirement to properly share the available bandwidth. So I would assume that you have very different applications running on the Wi-Fi network, from maybe I don't know, critical sensors to maybe people just having a quick look at a funny YouTube video sometime. So are you considering ways of prioritizing the traffic based really on the application itself? So
this is something that we are going to look at today. All the industrial, we force the user to put all the industrial and critical application on the wired infrastructure because we have the possibility to do that. So when we can't do that, we set up for the time being a dedicated infrastructure with a dedicated spectrum. And the idea we have is to merge the standard wireless connectivity from the end user, which are looking to YouTube, with critical devices. And this is for that we can define specific services with a specific type of quality of services. So we can, in the configuration, define that for general purpose services, they will have 50% of the airtime, for example, and for technical services, they will have 50% of the time. And if one is going to take much more, the system will automatically reduce the available bandwidth.
Okay, thanks.
No more questions? Okay. Thank you again, Sebastian.
Thank you.
Yeah. So I have a practical piece of information here. The dinner is tonight at 7:30 at the castle, and it's obviously in walking distance for many of you. But those who prefer to take the bus, there is a bus from the Scandic Hotel at 7:10, and there will be a bus from this premises at 7:20. So that's for all. Then it's a break. Thank you.